So next is common data for question number 15 and 16. An amplitude modulated station transmit a power of 40 kilowatt and uses a modulation index of 0.707 for sine modulation. The antenna is represented by 30 ohm resistive load. Question number 15 is the peak amplitude of the carrier before modulation, and question number 16 is the peak amplitude of the carrier after modulation. So it is given that the transmitter power is 40 kilowatt. An AM station transmits a power of 40 kilowatt. It means this is the total power transmitted, or the PT 40, and it is uses modulation index MA 0.707 for sine modulation, and the antenna is represented by 50 ohm resistive load. So antenna is represented by 50 ohm resistive load. So we can calculate PT is equal to PC 1 plus MA square by 2 we can apply, because this is sine modulation. So for sine modulation this formula is valid. We have to calculate peak amplitude of the carrier before modulation. So peak amplitude of the carrier before modulation matlab unmodulated carrier. So this is unmodulated carrier power. Unmodulated carrier power. So from this unmodulated carrier power we get unmodulated carrier amplitude, or the amplitude before modulation. Before modulation means carrier amplitude AC. So now we will calculate PC first. PC is equal to PT upon 1 plus MA square by 2. So PT is 40 divided by 1 plus, this is 1 by root 2, and the square of 1 by root 2 is 1 by 2. So this is 1 by 4, and we get 40 into 4 divided by 5, or you can write 32 kilowatt. So carrier power before modulation is 32 kilowatt, and PC is given by AC square by 2R. So this is 32 kilowatt, and AC we have to calculate, the resistance is 2 and 50, 2 into 50, and this is in kilowatt. So you can write 32 into 10 to the power 3. So we have to find the value of AC. After solving this you get the value of AC, which is 1788 volt. So this is the amplitude of carrier before modulation. Now the question number 16 is the peak amplitude of the carrier after modulation. So after modulation we get amplitude modulated waveform. So after modulation we get amplitude modulated waveform, and because this is a sinusoidal modulation we can have the figure of amplitude modulated signal like this. This is 0. This is the peak value of AM signal, and we have to find the peak amplitude of the carrier. That means this peak amplitude, which is denoted by maximum value of envelope, because this is the envelope and the maximum value of envelope is this, that is Emax, and this will be the minimum value of envelope, which is Emin. Similarly we have minus Emax and minus Emin, and we have to find the peak amplitude of carrier after modulation. So after modulation peak amplitude is Emax, and for sine modulation this peak amplitude is given by AC 1 plus MA. So we get AC, which is 1788, and 1 plus 0.707 modulation index. So we get the value as 3052 volt, which is option B, and 1788, that is also option B. So the answer for question number 17 and 18 is 15 and 16 is option B. You can find and check the answer. Okay. So this is the after modulation. And if we had to find minimum envelope or the minimum amplitude, if it is written here, the minimum amplitude of carrier after modulation, the minimum amplitude of carrier after modulation is E minimum. So it would have been AC 1 minus MA. So this is 1788, 1 minus 0.707, whatever will be the value, you can solve this. And we have the value of one carrier amplitude. So the average value of this maximum and minimum value is also carrier amplitude. So the whatever will be the value you will get in this after solving this equation, you can take the average value of E max 3052 and this value, and this average value should be 1788. And suppose we have to find the peak envelope power, and we have to find the peak envelope power. Peak envelope power. Suppose the question was to calculate peak envelope power, then this is AC square 1 plus MA whole square divided by 2. This is the peak envelope power, which is also known as PEP. Sometimes it is written like PEP. So AC square 1 plus MA whole square divided by 2. So you can remember this formula also. For sine modulation, peak envelope power is AC 1 plus MA whole square divided by 2. Now coming to the next question, question number 17. The amplitude of a sinusoidal carrier is modulated by single sinusoidal to obtain the amplitude modulated signal S of t equal to 5 cos 1600 pi t, 20 cos 1800 pi t plus 5 cos 2000 pi t, the value of modulation index is. So S of t is given 5 cos 1600 pi t plus 20 cos 1800 pi t plus 5 cos 2000 pi t. So this is the expression of AM in cosine form, that is sinusoidal modulation. So for sinusoidal modulation we have already derived the expression and we have used it before also. So this is AC cos omega ct, which is the carrier component, and AC MA by 2, which is upper sideband amplitude, omega c plus omega mt, and AC MA by 2, which is also the amplitude of lower sideband, omega c minus omega mt. We have these two equations, we can compare and find the value of modulation index. The value in the above expression which has same amplitude are the amplitude of sidebands. So the sidebands are having same amplitude. So here in this equation number 1, the amplitude of cos 2000 pi t and cos 1600 pi t are same. That means the value of AC MA by 2 is 5. And this is the value of AC, which is 20. So we can find the value of modulation index, which is 10 upon AC, which is 10 by 20, it is equal to 0.5. So the modulation index for this question is 0.5. Since it is a sinusoidal modulation, we can find the transmission efficiency, which is MA square upon 2 plus MA square, which is for 0.5. So 0.5, 2 plus 0.5, we have already calculated this, which is 11.11%. We can also find the message signal power. If we find the message signal amplitude, then we can find the message signal power, and message signal is written as, if we find the message signal, then modulation index is MA, which is given by AM upon AC. If the K is not given, then the value of AM we have to find. So modulation index we have calculated, which is 0.5, message signal amplitude is AM, carrier amplitude is 20. So we can find the value of AM, and AM will be 10. So message signal amplitude is 10, and suppose we have to calculate message power, which is sinusoidal wave. and having power, then it is AM square by 2. So, we can write 10 whole square divided by 2, which is 50 watt. So, this is the message signal power, modulating signal power. And if we have to find the carrier frequency, so the carrier frequency we can compute from this, because on comparing this we get carrier frequency which is 900 hertz, and this is your greater than carrier frequency. So, this is FC plus FM, which is upper sideband. So, upper sideband is FC plus FM 2000, that means this will be the 1000 hertz, and FC minus FM is 800 hertz. So, if we have to find the message signal frequency, message signal frequency is FC plus FM equal to 1000 and FM equal to 1000 minus FC, and FC is 900. So, we get message signal frequency as 100 hertz, and bandwidth of this AM signal is given as 2 times of FM. So, we can have bandwidth as 200 hertz. This may be another answer. So, these are the values which we can calculate from this given expression, and the question was to calculate modulation index. The answer is very easy, and that is 0.5. Next is question number 18. In a double sideband full carrier amplitude modulation transmission system, if the modulation index is double, then the ratio of total sideband power to carrier power increases by a factor of. So, we know that the ratio of total sideband power and carrier power is directly proportional to square of modulation index. We have seen that this relation, how this relation comes, and for sinusoidal modulation this relation is MA square by 2. So, if we increase the modulation index by a factor of 2, then this ratio will increase by a factor of 4. This is the 2 square, right. So, the answer is 4. So, we have to put the value of modulation index just here, and we get the ratio 4 times of previous one. So, it will increase the factor by, it will increase this ratio by factor 4. Next is question number 19. This is a common data question, question number 19 to 22. A sinusoidal the sinusoidal modulated double sideband full carrier waveform is shown in below figure. This minimum amplitude is given as 25, this maximum amplitude is given as 125. So, from the waveform of amplitude modulated signal, we know that because this is a sinusoidal modulation, we know that this modulation index MA is Emax minus Emin divided by Emax plus Emin, and it is equal to 125 minus 25, 125 plus 25, which is 100 divided by 150. So, this is equal to 0.667. So, this is the modulation index. Now, we have to find the carrier amplitude. So, the carrier amplitude is AC is equal to Emax plus Emin divided by 2. So, Emax is 125, Emin is 25 divided by 2, and this is equal to 75 volt. So, carrier amplitude and modulation index we can calculate from these two expressions. Now, we have to write the this is the question number 19, right. So, this is the question number 19, which is 66.7%. So, the answer is option C. Now, to write the expression of AM signal, we required carrier amplitude. So, we calculated the value of carrier amplitude, And because this is sinusoidal modulation, the expression will be in the form AC 1 plus MA cos omega mt into cos omega ct. So this AC is 75, 1 plus MA, MA is 0.667 cos of omega mt and cos omega ct. So according to this, the expression is option D. So option D satisfies the given expression. So answer of question number 20, this is the question number 20, is option D. Now next is determine the amplitude and phase of the additional carrier which must be added to make the waveform shown to attain a modulation index of 20%. So previously the modulation index was 66.7%. Now we want carrier amplitude, we want the modulation index to be 20%. So we want modulation index reduced. That means we have to increase the value of carrier amplitude, because we know that the modulation index is AM upon AC. So if we increase the carrier amplitude, then we get reduced modulation index. So for that we have to add some additional carrier. The word carrier is used here because we are going to use same frequency. The carrier frequency is FC, we are adding additional carrier, it means we are adding the same frequency but just the amplitude is different, because we have to add some value to AC so that this modulation index get reduced. Suppose I add this value X, then the modulation index MA dash definitely will be less than MA. So we want to add additional carrier in this term. So this S of t, if we add additional carrier in this term S of t, we get AC 1 plus MA cos omega mt into cos omega ct, because we have to add carrier, additional carrier. So carrier, that means the frequency will remain same, but we have to add additional amplitude. So let us say that amplitude is A. The amplitude we are adding is A. Now if we rearrange this equation, then we get AC cos omega ct plus AC MA cos omega mt into cos omega ct and A cos omega ct. So if we convert this equation in this form, then we can find the modulation index MA. So to write the equation in this form, we want 1. So let's write this whole term together, this first and last term together, we get AC plus A cos omega ct and AC MA cos omega mt into cos omega ct. So we want 1 in first term, so for that we have to take this whole term common. So if I take this term common, AC plus A cos omega ct, then we get 1 in first term and we get AC MA cos omega mt cos omega ct divided by AC plus A cos omega ct. So this cos omega ct and cos omega ct will get cancelled and we get AC plus A in bracket 1 plus AC into MA divided by AC plus A cos omega mt cos omega ct. So this is the expression. Now on comparing this expression with the original expression, this is the expression 1 plus this term. So 1 plus this term cos omega mt, and this is 1 plus modulation index cos omega mt. So the coefficient of modulating signal, the coefficient of modulating signal is modulation index. So in this expression the modulation index is MA dash, which is equal to AC MA divided by AC plus A. Now this new modulation index is 20%, that means 0.20, and AC is 75, and previously the modulation index was 66.67%, or you can write 2 by 3. Okay, so we can write 2 by 3 also from here. This is 50 into 2 and 50 into 3, so this is 2 by 3. So let's write 2 by 3 here, and carrier amplitude 75 plus A. So we can write this one as 1 by 5, and this is 150 divided by 3, 75 plus A, and we can also write 75 plus A equal to 250. So this is 175 volt. 250 minus 75. So the additional carrier has amplitude 175 volt, which is positive. So the positive value of carrier amplitude shows that phase shift is 0. Hence we can also write 175 at an angle 0. So it means that the amplitude of this carrier, additional carrier, is 175 and 0. That means the correct answer is option A. Now in next question 22, this is question number 22. Determine the amplitude and phase of additional carrier which must be added to make the waveform shown to attain a modulation index of 80%. So we now want the modulation index to be 0.8, 80%, that means 0.8, that means we want to increase the value of modulation index. So if we want to increase this value of modulation index, then we have to reduce the carrier amplitude. If we reduce the carrier amplitude, the modulation index will be increasing. So it means that the same additional carrier we have added and we get the same result, but this time in question number 22, so MA double dash is AC MA divided by AC plus A. This AC double dash is 0.8, 80%, and AC is 75, and this is 2 by 3, and the carrier is 75 plus A. So if we solve this, we get 4 by 5, 0.8, and this is 50 divided by 75 plus A. So this is 300 plus 4A equal to 250. So we get A is equal to minus 50 divided by 4, or minus 12.5 volt. So the amplitude, when it was positive, we take the phase shift 0, and if the amplitude is negative, then we take phase shift 180 degree. So we can write 12.5 volt is the amplitude and the phase is 180 degree. So the additional carrier we have added is 12.5 volt and phase is 180 degree. So the correct answer is option D for this question.